So here you're looking at a deep belief network. It's a hybrid model, right? You have a restricted Boltzmann machine followed by a sigmoid belief network. And a deep Boltzmann machine is a model that's just an undirected graphical model. So all the connections between latent variables here are undirected. So it's just a Markov random field with latent variables and dependencies between those latent variables, right? Whenever you're looking at inference in deep belief networks, the proper inference in deep belief networks is fairly problematic because of explaining away. Right? Typically, in order to figure out what's the conditional probability of this latent variable being on, you have to look at all its descendant as well as all of the nodes here, as well as what's happening upstairs and such. So in general, the inference process itself becomes fairly complicated. So what happens in practice is that people are typically using approximate inference that's fully factorized inference, like a mean field, a version of mean field approximation. Typically also, as I was mentioning before, when you're learning these models, most of the time you have greedy pre-training of these models. So you pre-train this module, then this module, and this module, and then you might want to fine-tune it for discriminative task like a neural network. But there is no joint optimization over all layers, right? That's something because inference in this problem becomes pretty complicated. And also, whenever you're looking at the approximate inference in this model, so when you're using these models for recognition and such, approximate inference is feed-forward. So conditional states of the visible variables, you just do a bottom-up pass, right? So there is no bottom-up, top-down effect in these models, okay? Whereas in deep Boltzmann machines, I'm going to show you that inference can be done fairly efficiently. We can optimize the parameters in this model jointly. And whenever we do inference, we can incorporate top-down and bottom-up. Okay. Okay. So let me give you a precise mathematical definition of what the Boltzmann machine models are. Again, we have exactly the same form. The probability of observed variable here, v, is given by this expression. Right. Now, what has changed from restricted Boltzmann machines? Right. What has changed is that we have these two additional terms. So this term here is looking at dependencies between H1 and H2, or latent variables in H1 and latent variables in H2. And the second term here is modeling dependencies between H2 and H3. Okay? So all we've done is we've introduced dependencies between hidden variables, specific dependencies between hidden variables. And all the connections here are undirected. So again, it's just an undirected graphical model. So from an interpretation standpoint, it's much easier to interpret. Now, if we look at the conditional probability of this hidden variable being on, right, or this hidden unit being on, it has this expression here. This is a sigmoid function. It's 1 over 1 plus e to the negative x. And the sigmoid function incorporates bottom-up, what's coming from below, and top-down, what's coming from above. Okay? And that just comes out of a specific definition of a Markov random field or Boltzmann machine in this case. And this is unlike many of the existing feed-forward models. If you're looking at convolutional neural network style models, or if you're looking at HMAX model of Tommy Poggio at MIT, or even in deep belief networks, typically inference in all of these models being done as a bottom-up inference. Okay? Now, we can look at the conditional distributions in this model. So we can define a set of conditional distributions. One thing that I should point out is that using Markov properties of this model, if I condition on H1, all the variables in H1, and I condition on all the variables in H3, then the conditional distribution over these variables in H2, it factorizes and can be computed in parallel. Right, so it's just given by the product of these conditionals. So we can define these conditional distributions. However, the problem here is that the exact computation of all of these latent variables, conditional observed variables, becomes intractable. Okay? And again, this has to do with the fact that we've introduced additional dependencies between hidden variables, so we're losing something. And we're losing in terms of doing efficient or exact inference. In restricted Boltzmann machines, we didn't have these additional layers, and inference could be done in closed form solution. But because we've introduced these dependencies, we cannot compute this conditional distribution exactly. So we have to approximate. Okay, so how does it compare to neural networks? Well, just a simple comparison. In a neural network model, you're typically going from inputs to the outputs. Okay, so you have to have a mapping x to y. So typically you have to have lots of labeled data to train these models. And also these variables here are typically deterministic, they're not stochastic. These models, on the other hand, they're trying to model the distribution of observed variables. Okay? If you're looking at a deep belief network, again, just to highlight the difference, you have directed piece here. And typically what happens is that if you want to do inference, you just reverse the errors and do some approximate inference using a neural network and such. Now, how do we do learning in this model, right? The model definition is pretty simple. How do we do learning? Well, if we look at the maximum likelihood learning, again, the maximum likelihood learning comes down as the difference between two expectations. Just as any type of undirected graphical models, factor graphs, conditional random fields, they all have almost the same learning algorithm or learning rule when you look at the derivative of the log likelihood function. The first term is, again, is expected sufficient statistics driven by the data, and the second one is expected sufficient statistics driven by the model. Now, the problem here is that now both of these expectations are intractable. Okay? And that's because, again, we've introduced these dependencies between hidden variables, so we cannot compute these expectations exactly. So what can we do? And actually should point out that there's been a lot of work, and I'm not really doing justice listing all of the work here, trying to look at how can we do learning in these models. It becomes fairly tricky. And if we look at the real world applications, typically we have thousands of hidden variables, or observed variables. We typically have millions of parameters. So we have to somehow be able to scale these models. And at the same time, if you look at a lot of previous approaches, a lot of these previous approaches were not quite successful when you're trying to look at Boltzmann machines or Markov-random fields where you have latent or hidden variables. So if you look at algorithms such as contrastive divergence, score matching, pseudo-likelihood, composite likelihood, piecewise learning, a lot of these algorithms that have been introduced in statistics and machine learning communities, they cannot quite handle models where you have hidden or latent variables. Okay, so what can be done here? So let's look at a learning algorithm. It's not a perfect learning algorithm, but it makes a somewhat step towards being able to learn these models. So the first thing that we need to do is we need to do inference, right? Condition on the data, I want to know the states of these latent variables. If I want to use this model for recognition or classification or regression, whatever I'm going to be using it for, I need to figure out what the states of these latent variables are. Oh, sorry.
Yeah, I'm just wondering if is it important that you still don't have any lateral connections in the model?
Is it important? No, the learning algorithm would imply even if you had lateral connections, it would be just much more expensive. Right, and I'm going to say where it will be more expensive. But yes, you can introduce lateral connections. But in this model, we're not, right? So the very first thing that we need to do is we need to infer the posterior distribution over these latent variables, right? So we somehow need to approximate it. Now, the second thing that we need to do is we need to approximate the joint distribution, right? And the way we could approximate the joint distribution is suppose that we're going to run a Markov chain. We're going to sample from the model. And suppose if we sample from the model, this is what we would get, right? Well, we could approximate data-dependent expectations by using some approximation inference here. We might be able to approximate data-independent expectations, and the goal of the learning rule is to match the two. So the idea you should have in mind is that, if you sample from the model, and this is what it looks like, right? Your learning rule will say, well, how can I adjust parameters of this model such that the distribution that I see here matches the distribution that I'm seeing here? It's a very simple idea. You sample from the model, look what it looks like, adjust the parameters so that next time you sample from the model, it kind of looks like the data, right? That's basically the idea behind the learning rule here. But if we look at these two problems are very different from each other, right? If we look at this problem, simulating from the model, and if we look at the joint space of hidden variables and observed variables, that space is huge. Imagine a space of all possible handwritten characters that I could generate, right? It's a very multi-modal probability distribution. It has lots of modes and such, and it's a very complicated one. On the other hand, if I look at this problem, then what I'm doing here is I'm slicing, conditioned on a particular instantiation of observed variables, right? I'm going to be looking at the distribution over the latent variables. Now, typically, if you look at this conditional distribution, you'd expect it to be unimodal, right? So if you see something like that, you might have certain ambiguities about exactly where pixels should go, but you'd expect it to be unimodal. Maybe you'd expect it to be bimodal, or maybe just few modes. Like if you look at the image and it's a very ambiguous image, and you could have two different interpretations of what's going on in the image, you could have two modes here. But in most of the situation, you only have a single mode, right? So this problem is much easier to deal with than this problem. Okay, so what can we do here? I'm very proud of that, though. What can we do here? Well, we're going to use variational inference. In particular, we're going to use mean field to approximate these expectations, or to do inference in this model. And we're going to use stochastic approximation, which is Markov chain Monte Carlo based inference procedure, to approximate these expectations. So in this particular model, we're going to be using two quite different techniques. And I'm going to try to justify why we need two quite different techniques for solving these two different problems. Okay? Now, before I get into what each of those steps is doing, let me just show you how you sample from the model, right? Suppose you want to sample from a two-layer deep Boltzmann machine. So the way you would sample the model is you randomly initialize the observed variables, and you randomly initialize the states of the latent variables at the second layer, and then you would just sample H1 here, condition on H2 and V, and then you'd sample H2 and V and so forth, and then you would just go by sampling it, right? The thing that I should point out here is that the conditional distribution of H1 depends on H2 and V. So this is where bottom-up and top-down comes in, okay? So now, let me just show you how we can use Markov chain Monte Carlo-based inference to approximate the second expectation, right? We're going to use something called stochastic approximation. And the stochastic approximation itself, it dates back to the works of Robinson Monroe back in the 50s. And it was actually originally proposed by Laurent Yannis in '89. And the funny story is that he wrote this paper in French journal, so no one knew about it. And then we've invented contrastive divergence and various approximations, and then back in 2006, Tayman basically reinvented what Laurent Yannis did 20 years ago, so we sort of circled around. But the idea behind stochastic approximation is fairly simple, right? Suppose that we have parameters in our model and we have states, right? We're going to update the parameters and states sequentially, okay? What we're going to do is we're going to generate X, right? All of the latent variables from some transition operator by simulating a Markov chain at least p theta some t invariant. What that means is that we're going to be running a Gibbs chain or a Metropolis Hastings sampler, whatever your favorite transition operator is, but let's say it's Gibbs. We're going to generate the state, and then we're going to update the model parameters by replacing this intractable expectation with a point estimate, an estimate that we get out of our Markov chain. Now, in practice, we typically simulate several Markov chains in parallel, so we're going to be approximating these expectations, these intractable expectations, by a sample average. Okay? Now, if we look at the update rule, right, the update rule can be decomposed into two terms. So the first term is the true gradient. This is what we want to compute. Okay? If we could compute that, we'd be in business. Okay? We could do maximum likelihood learning. Unfortunately, we can't compute this term. So we have a separate term, which is the difference between the true expectation and what we get out of the Markov chain, right, by sampling from the Markov chain, the sample average here. It's sometimes called the noise term. Now, there are certain theoretical guarantees. There are certain almost sure convergence guarantees. As the learning rate approaches to 0, you can show that you will hit the stable point. So you will converge to some stable point the algorithm will reach some stable point. Now, if you look at this expression here, it becomes a little bit tricky, right? Because this sample average is not unbiased, like in stochastic gradient descent. This is what we get out of Markov chain, and the samples that we get from our Markov chain, they're typically dependent. But the idea behind proofs of these different proofs that are out there is the idea that as your learning rate becomes sufficiently small compared to the mixing rate of the Markov chain, your Markov chain will always stay close to the stationary distribution that's sufficient to show convergence guarantees, right? So that's more theoretical argument. So it basically shows that, you know, in the infinite limit you will find the right solution. Now, of course, in practice, when we look at these models, we typically have high-dimensional data. If you look at the energy landscape, it's typically very highly multimodal. So what can we do here? Well, one of the things you can do is you can use other types of transition operators. So you can use more advanced MCMC methods. So for example, temporal transitions, parallel simulated tempering, to try to explore the space much more efficiently. Okay, but this so far represents a major limitation of these models. How can we search this space efficiently? And there's also nice connection to the theory of stochastic approximation as what's called adaptive Markov chain Monte Carlo methods. Okay, so but the procedure itself, when you code this up, it really takes 5 lines of code in MATLAB to implement this. It's not anything very sophisticated. The theory behind it gets fairly sophisticated, but the underlying ideas are pretty simple. Okay, so this is what we're going to do to approximate the data-independent expectations. Now, what can we do for inference in this model? Right? Well, here we're going to be using mean field approximation. As I was mentioning before, the idea behind mean field approximation is that we're going to approximate this conditional probability, which we cannot compute in closed form, with something simple tractable distribution Q. Right? And the same argument goes again. We look at the likelihood function. We can multiply, divide by the Q, parameterized by some mu parameters. We can use Jensen's inequality, and that comes out, just in terms of writing it up, comes out into variation low bound. This is the entropy functional. Now, the interesting thing here is that this log P star here can be expressed in this way, because it's a linear model. The log of the probability is linear. This normalizing constant, notice that that's the constant that gave us a lot of problems, right? You need to know this in order to compute this conditional probability. But notice that when you look at the variation low bound, we want to be optimizing with respect to Q distributions. This log normalization term doesn't really matter, right? So it drops out of variational inference. And that's where the power of variational inference comes in. We're looking for the Q distribution, and we don't need to worry about the normalizing constant of our original model. So we can perform this optimization tractably, right? And this is known as a variation low bound. So we're going to optimize this bound, maximize this bound with respect to Q distribution. And again, this can be written as a log probability minus what's called the KL term between Q and P. And just another way I should point out of looking at what the variation approximation does by looking at this expression, the variation approximation basically tries to minimize this term. And this is the distance. It's a form of a distance between two probability distributions. This bound becomes tight if Q is equal to P, right? Otherwise, this term is always positive, so you have a lower bound. And so you maximize this KL between approximating in the true distribution with respect to variational parameters mu. Now, if you choose a fully factorized distribution, if you choose a mean field approximation, right, you're just representing it as a product of factors, independent factors, so you don't assume any dependencies between these Q variables, then it turns out that you just define a set of fixed point equations, and these fixed point equations look exactly the same as the Gibbs updates, as your Markov chain Monte Carlo. So whenever you're implementing this algorithm, it's basically the same set of equations, nonlinear set of equations that you can loop through until you hit the convergence. Notice that the variation approximation, typically if you have a bimodal distribution, it will only pick one mode. So it will approximate any bimodal distribution just with a single mode, right? Now, so how does the algorithm work? Well, we do variational inference. We maximize the variational low bound with respect to the parameters, and then we apply Markov chain Monte Carlo stochastic approximation to update the model parameters. So for those of you who are familiar with EM algorithm, expectation maximization algorithm, it sort of has a similar flavor, where in the first step you're doing variational inference, you're trying to find approximation to the posterior distribution, and in the EM step, you're running MCMC and adjust your model parameters. You can also show, from theoretical standpoint, you can also show almost sure convergence guarantees to an asymptotically stable point. So you know that it will converge some point. It will converge of the variational lower bound. Now, two things that I should point out. Inference in this model becomes fast because we're using mean field approximation. Typically, for a full-size image, it takes a fraction of a second to infer, to find the mean field approximation to the posterior. And learning can scale to millions of examples because you're using stochastic approximation that's data independent. So you're just running Markov chains in the background and getting some statistics from the model, right? So it's fairly simple to implement this algorithm. But now the key question is, does it actually work? Like, is it a reasonable algorithm or not? And I'm going to let you judge whether it's a reasonable algorithm or not. Okay? So what I'm going to do is I'm going to show you two panels. On one panel, I'm going to show you real data, and on another panel, I'm going to show you simulated data or fake data simulated from the model, and you have to tell me which one is which. Okay? So these are just handwritten characters collected from around the world on Mechanical Turk. And again, one panel represents real data, one panel represents simulated data. How many of you thought this was simulated, this was real? Honestly. Okay, what about the other way around? Okay, so it's like 50-50, and the rest are unsure. That's good. So that means that I passed Turing test, right? So this is simulated data, this is real data. Okay, so if you look at a specific, like if you look at this handwritten character, right? If you look at it very precisely, you'll start seeing that there are just pixels missing at locations where they shouldn't be missing. Right? Humans wouldn't draw a handwritten character like that. And also notice that in terms of variety, there is much more variety in the real data than in simulated data. Right? And that has to do with the fact that when we're looking at the learning algorithm fails, at least at this point, to explore this highly multimodal distribution. Right? So we need better learning algorithms, basically. It does a pretty good job in terms of capturing the overall structure of how handwritten characters should look like, but again, it's a limitation of stochastic approximation and MCMC-based algorithms to explore it. This is another data set. This is MNIST handwritten characters data set that you've probably seen before. Again, it's the same story. How many of you think this is real and this is simulated? What about this is simulated and this is real? Okay, well, most of you probably worked with handwritten characters, right? Sometimes I can fool people who don't know about MNIST data set. You're right, this is simulated and this is real. And again, if you look at this 5 here, right? It's not quite as, a lot of people being thrown off by this 0, so they think this is simulated, but that's only if you haven't worked with this data set before. Now, in terms of recognition, you can ask how well you can do recognition, handwritten character recognition, or optical character recognition in these models. And again, we can do much better compared to deep belief networks or deep autoencoder style models, support vector machines and such. So they do a fairly good job in terms of recognition, as well as in terms of generation. This is a slightly more ambitious example where you have generative model of 3D objects. You have 24,000 examples, you have 5 object categories, you have 5 different objects within each category, different conditions, different lighting conditions, elevations, and so forth. And obviously you can see that this is real data and this is simulated data. And again, it does a fairly decent job in terms of capturing the underlying structure of what the data should look like, right? It's obviously, I like to point out that this example here, if you look at this example, it kind of looks like an airplane, no, it kind of looks like a car with wings, right? So what it does is that as it transitions from one mode to another mode, it can generate these hypothetical examples. So it's not just memorizing the data. The question you might be asking is that, does it actually just memorizes the data and then just spits out the data? No, it tends to generalize. You can also see that it's not obviously a perfect generative model. Again, it suffers from the same problem as exploring this complicated energy landscape. In particular, it tends to generate more people with guns, right? Like if you look at this guy and this guy and this guy and this guy, right? And not that many donkeys and elephants, right? So it's just only one donkey and one elephant. So what happens is that it puts much more probability mass on one class and not much on the other class. And again, it has to do with the deficiency of being able to explore the space efficiently. There's a question?
Is the problem with the sampling or the learning? So even if you learn the model perfectly, if you can't sample the you'll see the same effect.
I think it's the problem with learning. Because in this case, we've run the sampler for a very long time. I think we've run a sampler for 1 million steps before you generate these samples and such. So,
using the simple sampling method.
no, here I used more advanced sampling algorithm like temper transitions that tries to jump between the modes. So at this point, I don't think it's a problem with sampling. It's really a problem with the learning algorithm. not being able to explore the space more efficient. So we need much better learning algorithms, much better. And again, you're dealing with a very high dimensional problem. You have exponentially many modes. How do you explore these modes? It's a long-standing problem that's that I don't think it's an NP hard problem. So if someone comes up with a better learning algorithm, that would make a big difference. And again, here, if you're looking at recognition, a standard recognition problem, how you can recognize these models, we can do, again, better compared to deep belief networks, support vector machines, and some of the standard benchmarks. You can also do interesting things like pattern completion. So here I'm showing you objects that are test objects. These are the objects that the model has never seen before. These are new objects, okay? So, and these are the completions. So for example, if it sees half of a cowboy, it tends to basically say, well, if it's a human, it's got to have a gun, right? Because in the data set, all humans had guns, so there it is. And it does, completions for the airplanes and cars and such. So it does a fairly decent job in terms of figuring out what the remaining part of the image should be. These are the test objects. And if you look at the closest training example in the data, these are the closest training images, right? So one thing I should point out here is that if you look at this piece here and you look for the closest image in Euclidean space, it finds hippo. So if you did something naive like, try to find the closest nearest training example and just put half of it, then you would end up with half cowboy and half hippo. Or the same goes with rhino here. So again, it does find interesting structured data. It's able to do that fairly reliably. You can also use these types of models. Now, I've shown to you some of the models for image specific, but you can also use these models for other tasks like speech recognition, or in this case, keyword retrieval. And this was done by Yodong Zhang at MIT. And what he did was basically he had a timid corpus, 630 speakers, that many training examples and test examples, and his goal was basically trying to retrieve keywords. So they look at the speech, and if I say some particular word, they want to be able to retrieve it. So if you look at the speech and you say Russ, maybe you want to retrieve it. Obviously, you can see why it would be an important application. Particularly, I guess, if you're listening to someone's talking on the phone and such. And so they've looked at the standard models that people are using are Gaussian mixture models. It's the standard models that use in speech recognition. And if you look at the Boltzmann machine model, you can improve a lot in terms of what they call equal error rate and specific measure of error. And the other interesting thing is that they've noticed that if you add labels, right, 1% of the label, 30% of the labels, you can further improve the results. So this is where the semi-supervised aspect comes to it. If you have a few labeled examples, someone marks the keywords, you can really improve things here. And again, it's exactly the same model as I was talking before. Now, let me just get into a couple of more advanced models. Where you're looking at, you're trying to combine both directed and undirected models, but also trying to look at more advanced models. So this is the model where you can try to deal with occlusions or structured noise, right? So in particular, imagine that you observed an image like this one, and what you really want to do is you want to infer the face, and you want to infer a specific occlusion of that face. And that becomes fairly important for applications such as recognition and such. You can define different energy functions. So this is particular energy functions that Charlie Tang at University of Toronto was looking at. The idea is that you're going to be using Gaussian RBM, and later on he was extending to using Gaussian deep Boltzmann machines. So you can obviously have multiple layers if you want to. You have a Gaussian RBM modeling clean faces, that piece here. You have binary RBM modeling the occlusions. So in particular, if these are structured occlusions, you can try to model what they look like. You have a binary pixel-wise mask. The mask is effectively saying which pixels belong to the true face and which pixels belong to the mask, right? And then you have just a Gaussian noise on the model. So it essentially says if the mask is off, basically, then whatever you put in here doesn't really matter, right? It could have a very high variance. So it's a very natural, very simple definition of the energy function. And again, you can define these models to be to have more layers and such, but you just specify here the image formation process of how mask and the actual clean face interact together. And there's been a lot of work, also related work from other researchers trying to deal with this issue of whenever you're trying to build something robust, right? So here's one example where if you're looking at robust Boltzmann machines, these are the observed data, and this is what the model infers as the learning procedure. So it basically says, I believe the clean face should look like this, and this is what my structured noise is. Notice that it also thinks that there are a few pixels in here. Like his hair doesn't look quite right? So the model says, no, it's not quite right. You know, you can do at the test time, right? If you have a person like this is a test image, it infers the clean image, basically removes the eyeglasses. Or if you have a scarf, it removes the scarf. And again, you have just two models, one model in clean faces. It basically says how faces should look like. And the other one is trying to model structured noise. So if you have structured noise such as eyeglasses or scarves or specific shapes, the model can pick up on that during the training stage and figure that out. And you know, if you're trying to do, you know, if you have a noise like this, corruption of the noise, and you look at various other denoising algorithms such as PCA, notice that RBM does pretty bad job in terms of denoising. So you need something more than that. Again, this is just a very simple model, but I want to emphasize that once you go beyond the standard model, you can start adding some prior knowledge about how images are formed or what kind of noise conditions you're expecting to see, and you can model that. Okay, so there's some prior knowledge that you can put into the model. Here's another model called Deep Lambertian Network. Again, it was done by Charlie Tang, and it's again another idea where you're trying to combine undirected model with directed model. So it's in a flavor of a deep belief network, but it combines a nice properties of what's called Lambertian model with deep belief networks and deep Boltzmann machines. Right? This is the example where you know, one question that typically arises when you look at these deep networks is that how can I put prior knowledge into the model? So in this case, if I know specifics about how images are formed, I can incorporate that. Right? So here's the idea. You define the likelihood function. It's just a bunch of product of Gaussians. Oh, sorry. Right. The Lambertian model, I should just emphasize that it's a specific model that's coming from computer vision community, how images are being created. And the idea is that you have something that's called albedo, which is diffuse reflectivity of the surface. It's material independent, but it's illumination independent. And that's something that you want to extract in order to do recognition. Okay? So the idea is that we're going to define the likelihood function. The probability of observed input is being formed by a Gaussian model, right? And we have image-specific albedo, we have surface normal, and we have light source. And notice that the surface normal interacts with the light source, and then you multiply it by albedo. Okay? That's a very specific model. You can think of it as just multiplying three components together. Now we can put the prior on albedo and surface normals and the light. In this case, we're putting Gaussian restricted Boltzmann machine priors on these forms and just the Gaussian prior on the light source. And you can also put some of the better working models if you put deep Boltzmann machine prior on the albedo and surface normals or deep belief network prior. Again, you can play with these models as you go along. Inference is typically being done with Gibbs sample. Learning can be done using stochastic approximation, just as you would do with deep Boltzmann machines. And again, so this is just to show you what the data sets look like. You know, if you look at something like that, right, you have extreme variability in light. The question is, can you recognize the face here? So here you have 38 objects, you have 45 images with various illuminations and such. You have 28 objects for training, 10 for testing, and you can use Toronto. We actually use Toronto phase database to pre-train albedo deep belief net. Okay, so you can create some prior knowledge about how faces should look like, right? And this is what's happening at the test time. If I show you that image, this is the albedo, and this is surface normal, right? If I show you this face, this is the, if I show you just two faces of the same person under different light conditions, this is the inference of that face. And this is what you can do. You can also do fun things like face relighting, right? It's always fun to do. Like, one nice thing about building generative models is you can generate things, and it's a lot of fun when you generate things, right? So this is inferred albedo, and then you can generate the same person under different light conditions. And obviously, if you want to do face recognition, instead of using these as your input images, you'd want to use that as your input image, right? Obviously. And this is just some results showing that, you know, if you use deep belief network or nearest neighbors, these models are terrible for these types of data because you didn't put any prior knowledge about how images are formed. And this is the deep Lambertian network, and this is something that we call one-shot recognition. Just based on a single example, you can start doing recognition and singular value decompositions. Once you get 5 or 6 images, this is a standard model, singular value decomposition, doing recognition here. You know, you can also apply the same type of model to other images. So these are just images of cups and so forth, and these are the albedo extracted from those images. So again, it's just one other interesting extension of these deep models, deep network models, but in the cases where you can incorporate prior knowledge about how images are formed if you're trying to do recognition, okay? Now, finally, let me just finish off by saying a few words about multimodal inputs, or learning from multimodal data. One of the exciting things about deep networks and restricted Boltzmann machines and deep Boltzmann machines is that you can deal with a lot of different input domains, right? You can deal with images, you can deal with text, you can deal with speech, you can deal with videos, right? By using different members of, by using different probability distributions, domain-specific probability distributions that are, at least within exponential family models, you can try to model all of these inputs together jointly, right? And this is something unique to these models. And of course, ultimately, we all want to develop learning systems that come closer to displaying human-like intelligence, right? And obviously, as humans, we don't only look at static images all our lives, right? We look at video and text and speech, everything comes to us. So there's one particular way of doing that, which is a very simple way and, you know, a very straightforward way, is to form a big model where you have video, text, speech, and you have separate pathways of extracting video, text, and speech, and then do joint modeling of all of these sources together, right? And you can be more robust at perception, you know, and there's been some work by a group from Stanford at ICML that used deep autoencoders by trying to model video and speech. There's been other works trying to basically look at the images and text and such. And we've been also trying to look at images and text. And you know, imagine you have a data of this form. You have images, and this is the text. It's not a very useful text. Some images don't have text, and some images, again, have just random text. These texts are reasonable. And now the question is, can you take this multimodal data and build a model if you want to, for example, recognize what's going on in the images, right? So where can it be used for? Well, for one thing you can use is maybe it will help you to improve classification, right? Obviously, you have additional source of information that should help you improve classification. You know, you can use it for filling in missing modalities. So you might get a description of what's going on in the image. I show you an image like this, and it might say, well, this is what beliefs it sees in that image, right? Or you can do retrieval from one modality when you're giving it query from another modality, right? So if I type this in, maybe I want to get something like that. Okay? So one of the things that we've been looking at, a multimodal deep Boltzmann machine. Here you have image, you have text. For text, you can use replicated softmax model. This is a multinomial Bernoulli RBM, essentially, very similar to the one that you can use for collaborative filtering. And to model the image features, you can use Gaussian restricted Boltzmann machine. So again, you can mix different modalities together and build a joint model of this form here. Sorry. Right. So this is based on the Flickr data set. you have 1 million images, you have about 25,000 annotated images. Now, the interesting thing here is that you have access to 1 million images, right? So when we started looking at the literature, a lot of people would just throw away these million images and just use 25,000 annotated images because you need labels to build these models. Whereas with our model, you can use unsupervised pre-training, so you can use these 1 million images to learn a good generative model of images, and then you can use text to learn a good generative model of text, right? So that comes, it's a big advantage if you have unlabeled data, in our model at least. So this is an example of I guess, completion, generation of the tags. You have these images, these are what the tags that were given to us. These are test images, and this is what it generates. So in some cases it generates reasonable things. It does tend to figure out what's happening in the images. This is an example where given an input text, you're trying to do image retrieval, right? So these are the two nearest neighbors to the generated image features. So condition on the text, you generate images, and then you're looking at the closest images in the training set. So these are the closest images that it finds given the text. One interesting thing about recognition results, if you look at different learning algorithms, if you look at support vector machine and linear discriminant analysis, the deep Boltzmann machines does much better in terms of mean average precision, so in terms of retrieval results or recognition results. It's also interesting to note that if you're just using image-specific models, so if you ignore text, so if you ignore one modality completely, your results become much worse for whatever algorithm you're using. So that's quite important because it's telling us that if you have extra sources of modalities, they tend to help, at least on that particular task. Okay, so it's very important in trying to model the joint distribution over different modalities, if you can. You can also do things like retrieval. So if I show you an image together with captions, then this is what it retrieves, the 4 retrieved results. Or if I show you this image with captions, this is what it retrieves. So again, in most of the cases, it does a reasonable job. I also like to watch at these things. This is given a test image, you generate associated text. So again, if you look at the text like this one, it does a decent job in terms of generating the text. I like this one. So it does, you can obviously see where the confusion comes in, right? So if you look at this horse, it says expression, lady, look, human, gorgeous, portrait, person, blonde, right? So it's a blonde, right, gorgeous. So obviously this comes from Flickr dataset. Most of the people just have portraits and very few horses, I guess. So the model confuses it, right? And of course, some of the cases, like if you look at this image, it doesn't quite capture the right structure. So if you look at this image, it says it's a car. It has to do something with the car. Again, there's probably a bias in the Flickr data set. There are lots of cars people uploading, right? And not that many images of this form. So yeah, there's a question. Well, in this model, this is the model, right? A few more layers, or like meaning here, yeah, it could be. We haven't done it. It could improve results, but this is something that has to do with model selection that I want to briefly address before so maybe I could just finish and then we could go through questions if that's okay. Yeah. So finally, just one quick thing that I wanted to point out is the question of model selection, right? So this question comes up in a lot of cases. How many layers you should have? How many number of hidden units you should have? How can you choose between different models? How do you know maybe you can add more layers and such, right? So these are or in more general, how can you compare it to other models, right? So this is an example where if you look at deep Boltzmann machine samples of MNIST digits and you look at mixture of Bernoullis, how do you know that this model is better than this model, right? So one way of achieving it would be to compute P of V on some validation or some test set, right? And once you know the probabilities of observed inputs, then you can obviously make a decision which model is better. But in order to do that, you need a good estimate of the normalizing constant, a good estimate of the partition function, right? So there is one thing you can do is we've been looking at MCMC-based algorithms for estimating normalizing constants, particularly using something what's called annealed importance sampling, and that's something that's going to be covered in one of the classes, one of the tutorials, one of the lectures when you start talking about Markov chain Monte Carlo methods. It's a fairly advanced techniques, and I just can give you a brief highlight of how it works. The details are fairly complicated, but the idea is that you start with something simple, a base model, right? This is your base distribution, which could be a uniform model, it could be an independent model, and you define a sequence of models that transition from this base model to your advanced model. And you go through a sequence of fairly simple models until you get to your complicated model. And the idea is that you're estimating this ratio of normalizing constant. You know what this normalizing constant is because it's a simple model. And then you estimate this ratio of normalizing constants by going through a sequence of ratios of normalizing constants where they're pretty close to each other, right? So again, this has to do with the idea that you're trying to take your complex problem and trying to decompose into a series of simpler problems, and you can solve each one of those simpler problems approximately, and when you combine the whole thing together, you get a solution. Okay, so now if you look at DBM samples, you have the test log probability for mixture of Bernoullis is about 137 nats, but if you look at the deep Boltzmann machines, it's about 85 nats, which is quite big. A difference of 50 nats is striking. So 50 nats basically means that DBM is e to the 50 times better than mixture of Bernoullis. So e to the 50 is roughly the number of particles in the universe or something like that? So by that much better than mixture of Bernoullis. Right, of course I'm exaggerating, but this is what it says. So again, when you're doing model selection, one thing you can do is you can have a set of different models, like 10, 20 different models. You can try to use these techniques, annealed importance sampling techniques, trying to come up with a good estimate of the partition function and then do model selection based on that. So this is task-independent model selection. You're not specifically choosing that one model is better at discriminating than another model. You're just trying to figure out which model models the distribution of the data better and doing validation based on that. And again, I should point out that you will hear about advanced MCMC techniques, in particular using model selection for these deep networks through one of the lectures. Okay, so let me just finish off by saying that insofar everything that I talked about today had to do with the case that you find these edges, you find combination of edges, and maybe you can start finding high-level representations of object parts as you go high up in the hierarchy. And if you look at deep belief networks, deep Boltzmann machines, it really has to do with learning hierarchical structure in features, right? Edges, combination of edges, they get put together. So you can call it as a part-based hierarchy, right? The interesting thing is that it performs in many application domains, it performs fairly well. So the work, for example, in speech that I was doing with MIT people, I don't know anything about speech. They have their own complicated algorithms using 50 cluster machines and doing all kinds of crazy stuff, but if you substitute one module, Gaussian mixture models, with a deep Boltzmann machine, the remarkable thing is that the people who don't really know about these models can just plug them in and get results, much better results. It's quite exciting. You have a natural notion of combining bottom-up and top-down. You can do fast inference because you're using mean field approximation, using variation approximation. Again, it takes a fraction of a second to just cycle through the equations and get a fixed point solution. And this is quite important because given an input, I really want to know the answer. I can't wait for a very long time. So this was the justification for using variation inference as opposed to doing MCMC. You need the answer fast during inference. And during learning, the learning can scale to millions of examples precisely because you're using stochastic approximation, MCMC-based inference. But insofar, I've been focusing on the examples where we have many examples in few categories. Right? You have thousands of examples, but maybe 5 or 10 different categories. Right? And next, what I'm going to be talking about tomorrow is the idea of something that's called transfer learning. something where you have many categories but few examples within each category, which is a very fundamental problem in statistical machine learning. Sometimes it's also called one-shot learning. Okay? Let me just give you a preview and I'm going to be done. Suppose you're looking at these handwritten characters, right? Now suppose I show you that this is called Zark, right? Can you find me other Zarks? So for example, would you say that this is a Zark? Yeah. What about this one? Oh, this one? What about this one? Yeah. So just based on one example, you basically got the concept, right? Whereas in the previous cases, if I, for handwritten characters, for example, we have 2,000 images of 2s, right? Or 3s. So if I give you 10,000 images of 5s, right? Then we can learn what 5s look like. But that seems ridiculous, right? Like for human learners, if I show you 5, maybe 4 examples, 3 examples, you can get the underlying concept and start generalizing, right? And this is the same example here. If I show you just one image of a segue, you can basically get the concept. You don't need 2,000. You don't need to look at 2,000 images of these segues to figure out what they look like, right? And this is one of the fundamental problems, is that how can you learn a novel concept which is high-dimensional statistical object from few examples, right? And this is the problem that has to do with the transfer learning problem. It pops up a lot in various application domains, okay? And this is just if you look at the traditional supervised learning problem, something that you've seen in this summer school is that I show you a bunch of segues, I show you a bunch of motorcycles, and I can ask you what that is, right? It's still a very hard problem. It's still not a solved problem. But this is the type of problems that you're mentioning it. But one other thing that you can do is you can try to say, well, suppose we have millions of unlabeled images and maybe some labeled images. I show you a few dolphins, I show you bicycles and so forth. Then the question is, if I show you a single image of a segue, can you basically learn this concept or this class from one example, right? And then start testing what that is. So this is going to be the theme of the talk tomorrow. And this is the key problem in a lot of application domains. Okay, so thank you. And I should also point out that the code for learning restricted Boltzmann machines, deep belief networks, autoencoders, deep Boltzmann machines is available. Oh, I should change the affiliation here. It's available on my webpage. And there's a MATLAB code which you can download it, put demo. And so, for example, for MNIST handwritten characters results, you can reproduce state-of-the-art results if you just run the demo. So you should be able to figure out how to use mean field inference, stochastic approximation, everything. It's not very complicated code because I'm not a very good programmer, so my code tends to be fairly short. As soon as it gets fairly big, I don't want to do that. So it, it's fairly simple to implement these models. That's another good thing about these models. Thank you.